Hi, welcome to the video about balanced forces. And so I hope by the end of this video, and I'll try to keep it short, that you can tell the difference between whether forces are balanced or unbalanced on an object, and you can figure that, and also you can figure out how that works with whether it's going at a constant velocity or whether it might be speeding up or slowing down. So the first thing is a term. I like to use the word force diagram. Other people like to use the word free body diagram, and I'm just going to tell you it really means the same thing. So I'll use force diagram. Here's the big thing to remember. If the forces are balanced, then the object is moving at a constant velocity. It might be a constant velocity of 0, but it's going to be moving at a constant velocity. If the forces are unbalanced, so in other words that they don't all add up to 0, then the acceleration will be in the direction of the net force, or you could also say of the unbalanced force. So whichever way, if you consider how much they do cancel each other out, if they don't completely cancel each other out, whatever you're left with at the end, that's going to be the direction of the acceleration. Not necessarily, it won't necessarily be moving that way, but it'll be accelerating that way. First example is, we'll try to keep it real simple, is a book rests on a desk. So if I were to draw the forces acting on that, there'd be a force of gravity, right, on the book by the earth, and there'd be the desk. This would be a normal force on the book by the desk. And I put those equality marks in there to say that it is balanced. Okay, constant velocity of 0, not accelerating. A book is pushed on a table at constant velocity. Okay, so let me just see if I can copy this. Alright, so I did a copy and paste there, but the thing I need to add is the fact that somebody is pushing this book, so I will add an applied force here to the right by, I don't know, who's pushing it, by hand. Sorry, I usually do the on first. On book by a hand. Now at that point, if I stop there, there's no way this would be a constant velocity, because right now it's unbalanced, and if it's at a constant velocity, that means that they need to be balanced. So how would I balance it? Well, there must be some force that is equal and opposite in this direction. And if I think about the situation, right, of a book being pushed along a table, it's probably the force of friction. So I'm going to say the force of friction on book by, and that is the interaction between the table and the book. So by table. And I'll put 2 ticks there to show that that is equality, equal. FA and FF are equal. Okay, for example number 3, it says, which way is the object moving? And the temptation is, and you're looking at it, you're probably thinking it right now, the temptation is to think that it's moving to the right. But the answer is, we don't know. Which way is the object accelerating? We know this one, and is accelerating to the right. Is it balanced or unbalanced? Unbalanced, because if we add them all up, it's unbalanced, and I'll say that the net force is to the right, where I might say it is unbalanced to the right. The word net just means the result of adding things together. So when I add these two together, they cancel out. When I add these two together, I get a rightward force. So the net force is to the right. Speeding up or slowing down if moving to the right. Well, if it's moving to the right, then it would be speeding up. If it was moving to the left, then it would be slowing down. So there is an example of, we don't know just from looking at the forces which way it's going. It could be moving to the right, speeding up. It could be moving to the left, slowing down. It could actually also have some vertical motion that is happening in this situation. Example number 4 is a table here, and it says there's time and position. Which direction is it moving? Well, let's think. If I drew a kind of a motion map here, and so if I use the convenient grid marks here, and if I say, okay, at position 30 is where it starts, and then a second later it's at 20, and then a second later it's at 12. Each one of these ticks is 2, so that'd be over there. And then it's at 6, 2, 4, 6. And then it's at 2, and then it's at 0. Now when I draw my arrows that are going halfway to the next one, these would tell me the velocity each time, so I'm drawing these in here. Pretty clear to see that we're having changing velocity, aren't we? I could say changing velocity. So that means acceleration, and that means unbalanced forces. Okay, little exclamation marks. Which direction is it moving? Well, now that I made the motion map, it's a lot easier to see the fact that it is moving to the left, or we could say in the negative direction. Is it speeding up, slowing down, or a constant speed? It is slowing down because it was going quickly. In the first second, it averaged 10 meters per second. At the end, it's only averaging 2 meters per second. So I'm going to say it is slowing down. What is the acceleration? I don't think we can get an actual number necessarily here. I think the acceleration is negative. Is it balanced or unbalanced? Unbalanced. Any graphs you could make? Well, let's just see. Could we make a position time graph? And all the numbers are positive, so I'll just go like that. So a position time graph, we would start at 30. No, here's 30. We'd end at 0, and our time goes up to what, 5? So kind of go like this, right? We have that curve that way. We could make a velocity time graph, and our velocities are all negative. And here's 0. So we would start with a large negative velocity and moving up towards 0 at the end. I'm not sure if it stops at that time. It kind of, my intuition says that it's going to stay at the origin at 0 for a little while, that it is just stopped. So I'm going to put that there, but you don't really know for sure. You could make those two graphs. Is that it for our, yeah, that's it. So I hope that makes sense. Yeah, I hope that makes sense for your identifying balanced and unbalanced forces.